Hello. In this video, we will show how to take an angle and a magnitude and turn that into a vector. We will also show how to take a vector and break it down into its angle. There is a separate video which covers how to find the magnitude of a vector. So let's start with the following example. Let's say we are told that a ship is heading at 40 miles per hour directly northeast. If we establish the eastern direction as 0 degrees, then that means our ship is traveling at 45 degrees, since we count angles in a counterclockwise manner. So great, we now know that our ship is going at 40 miles an hour, which is a magnitude, at an angle of 45 degrees, which is a direction. So this is a vector, since it contains both magnitude and direction. But let's say we want to express this vector as we usually do, in terms of an x and a y component. Well, we can do this with some basic trigonometry. First, I should point out that since the eastern direction is 0 degrees, the eastern direction also corresponds to positive x, and the northern direction corresponds to positive y. So, to write our vector in terms of x and y, we need to know what the x and y components are. The only information we have to work with is the magnitude and the angle. We can always make any vector into a right triangle where the vector is the hypotenuse. The other two legs will be our x and y components. So now we just need to use trig functions to solve for x and for y in terms of the magnitude and angle, which are known. I suggest you pause the video here and try to come up with the correct expression yourself. Okay, so now we'll do this together. First, let's try to find the x component. We need a relationship that connects the x component, which is adjacent to the angle, with the angle and the magnitude, which is the hypotenuse. Looking at the list of our trig identities, can you figure out which one will be most helpful? If you answered cosine, then you are correct. Cosine of an angle equals the adjacent over the hypotenuse, which in our case is the x component over the magnitude. So this gives us an equation that contains the x component as well as two things that we know, the angle and the magnitude. So now we just solve for x by multiplying both sides by the magnitude. We find that x equals the magnitude times the cosine of the angle. Great! Now we know how to get the x component for any vector. Plugging in the values for our specific problem, we find that the x component equals 28.3 miles an hour. Next, how do we get the y component? This will be very similar. We have to choose the trig identity that will be most helpful. Please pause here and think about which one that will be. Okay, so if you answered sine, then you are again correct. Sine of the angle equals the opposite, which is the y component, divided by the hypotenuse, which is the magnitude. We solve for y, and we find that y equals the magnitude times the sine of the angle. Plugging in our values, we find that the y component is also 28.3 miles per hour. For the special case of a 45-degree angle, the x and y components will be the same. Hooray! We now have the power to take any angle and magnitude and turn it into an x and y component. So now we know how to compute the x and y components from the angle and magnitude. Next, we will try to compute the angle from the x and y components. This part is a bit trickier. Imagine that we fire a cannon, and we know that the cannonball's initial x velocity is minus 10 meters per second, and its initial y velocity is 20 meters per second. What angle was it launched at? Again, we will draw a triangle out of a vector, where we know what the x and the y legs are. We then mark this angle here as the angle that we are looking for. Now, we want an expression that relates the angle to the x and the y components, which are the adjacent and opposite components. Can you figure out which property we will want to use? That's right. Let's use tangent. Tangent of the angle equals the opposite over the adjacent, which in our case is y over x. So now we have an expression, and we just need to solve for the angle. The question, though, is how to solve for the angle, since it is being acted on by a tangent function. Well, there is a function called arctangent, or inverse tangent, which, when applied to a tangent, undoes the tangent function. We would write that like this. This is very similar to the way that dividing by 2 will undo the act of multiplying it by 2. So if we apply the arctangent function to both sides, we will be left with this formula. The angle equals the arctangent of y divided by x. Great! Since arctangent is a function that is available on your calculators, computers, and programming languages, we now have a very easy method of obtaining the angle. Just use this formula. There is a problem though. Arctangent will only ever return angles within the range of minus 90 degrees and 90 degrees, or the right half of the coordinate plane. And it will never return a value between 90 and 270 degrees, or the left half of the plane. So that seems like a problem. How are we supposed to know if really our angle was something on the left side of the plane, and if it is, how do we figure out what the angle should really be? So this is what we should do. Before putting the values into the arctan function, we should look to see if we think our vector is on the right or left side of the plane. This is done simply by looking at the x component. If it is positive, then our vector is on the right, and we can just run the arctan function on our values and use the result. If it is negative though, we have to do a tad more work. Basically, if our vector is on the left, then the angle we get from the arctan will be in the exact opposite direction of the true vector. So for instance, if our vector is pointing in the top left quadrant, as it is by our cannonball, then the angle we will get out of the arctan function will be pointing in the bottom right quadrant. This is an angle shift of 180 degrees. So if you need to shift an angle from the right side to the left side, you just need to add or subtract 180 degrees, whichever will give a value between 0 and 360. So I know that this all sounded complex, so let's explore this with our cannonball example, and you'll see that it's really not so hard. We notice immediately that our vector is pointing to the left, so after putting our x and y values into the arctan function, we will need to shift the result by 180 degrees. So let's see what the result is for arctan of 20 divided by 10. The result is about negative 63 degrees. So in order to get a nice value between 0 and 360, we will add 180 degrees and get 117 degrees. Indeed, that angle points pretty close to where we would expect, and this is the angle that our cannonball is fired at. Thanks for watching.